Hey, well, welcome here. We are going to do our first remote lab. And I'll begin by saying today's lab is tied with the lecture on Chapter 2, which then probably makes more sense for you to watch the lecture on Chapter 2. And so in these videos that I sent out here today, the first one for the lecture is on Chapter 2, which is on the idea of distance and speed and velocity and acceleration. So if you haven't already studied Chapter 2, do that first. And that will give you some background into the lab we're about to do. Okay, so pause, go look at Chapter 2. All right, so I'm going to assume you've already done Chapter 2 here, and so let's go ahead with the lab. And like I said, Chapter 2 is about speed, velocity, and acceleration, and that's what today's lab is. It's a chance to, and if this was face-to-face, I would say, get your hands dirty yourself and see if you really understand the concept of speed, velocity, and acceleration. So we're going to do a little lab together, and our remote labs are obviously a little different. And as I mentioned on the first day, here's how I'm going to treat the labs. I'm going to pretend that I'm your lab partner. Because in a normal lab setting, what would happen is I would group you guys into groups of 2, and then I would say, okay, you and your partner, you go out and you work the equipment, you collect the data, you then analyze the data, you then answer the questions at the end, and that's exactly what we're going to do. The only difference is I'm going to be your lab partner. I'm going to be the one collecting the data. You're going to be the one writing the data down. And so we're going to work as a team here. And so by watching the video, you'll kind of watch me with the equipment. This first equipment's pretty straightforward, as it should be. The first lab, pretty straightforward, as it should be. And so let me just begin. And so I'm going to grab my lab manual, and you grab yours, either probably in your case it's in the PDF format. That's what I sent out on an earlier email. But here's the lab manual, and as we talked about in the syllabus, the first lab is the motion lab, and I believe that's page 8. Let me just look at the table of contents. Motion, yeah, page 8. And so let me flip over here to page 8. And so what you're going to want to eventually do here is, is grab this page 8. You can even read through page 8 if you would like, but this is what we're going to do together. And so I'm going to just follow these procedures right here that says, okay, make these measurements. Page 9 is where you're going to write it down. And this is the part where you will probably have to then print page 9 so you can write it down and then scan it back into the computer later on to turn in on Canvas. In fact, there are ultimately 5 pages that you're going to turn in. This first one will get started. This is the raw data. But then, once we get the raw data and do some calculations, in order to look for patterns, we're going to make 3 graphs. This is the first graph. Oops. Right here. And this is going to be your second graph, page 12. And your third graph and final graph, page 13. And as you plot the data on here, there will be patterns that form, and that will allow you to answer then these 9 questions. And so every lab is going to work like that. There's going to be a collect the data. That's what we'll do together here in video. Then you'll analyze the data, and that's what you'll be doing on your own. You'll make the graph, do some calculations, and then you'll also answer some questions. And so, again, let me point out, it's these 5 pages that you're going to scan and turn in on Canvas on that place where I showed you the assignment. Now, I'll say it again, I gave you and myself a big window of opportunity here. Nothing is actually due until June 1. There's still some things I have to set up in Canvas, and of course, you've probably got to learn it. But I think this first lab, when you get it done, would be a good experiment for you to turn it in on Canvas. Because what hopefully you have learned before the test date on June 1 is how to turn things in Canvas. Because when it comes to the test, you just have that hour-and-a-half time limit. You got an hour and 15 to do the test, and then you got 15 minutes to scan it and post it. And I want you to have as much experience, and so experimenting with Canvas is really good. And that's what these labs will do. And so between now and June 1, we will be doing 4 labs. We've got 2 this week, and remember, next Monday's a holiday, so then Tuesday and Wednesday, we've got 2 other labs. All right, well, let's get started then with today's lab. And so as a team together, let's collect our raw data here. Now, so you can see this a little better, I'll put some things here on the board. And so I'm just going to take this table and say, okay, the first heading is delta T. I'll talk more about that in a second. The next one is just T itself. The one after that, unfortunately, is an old notation of S. Let me mention that one in just a second. Then there's a delta S. Then there's a V bar. And then there is finally a T squared. And so again, you don't have to write on the board. I'm just trying to get it so you can see it a little bit better. But we're going to fill in this table. And here's the gist of today's experiment. We're going to work with motion. And what we're going to do is we're going to put an object, up in the air a little bit. It's not real high. As you'll see, the object looks, I guess it looks a little pointy on one end and kind of flat on the other. But I'll just make my cylinder. That was probably would look better if I did that. You like that drawing better? No.
It's just too high, but sweet.
Oh, a little too high? Okay,
let
me come down here. I'm trying to remember what our object looked like. I think it is. It's pointy on one end. And then it's a cylinder down here. Something like that.
Yeah.
All right. So it really doesn't matter what we have. But as you saw, hopefully, in the lecture part of this, is we're going to do what we call a free fall. We're going to drop the object. And the object is going to fall. And it's going to start here and go faster, 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 faster. And these dots are supposed to represent where this object is every 30th of a second. And of course, I haven't done the experiment. It's actually just right behind the camera, so I'll go over there in just a second. But when I get to the experiment, you'll see here that our equipment allows us to mark where is this object every 30th of a second. Now, let me just pause with the symbol. As you saw in the lecture here, we like to use the symbol T for time, and a new symbol here is this Greek letter delta. It means the change in time. And so as I go to the equipment here in just a second, and you and I perform this experiment together, what we're going to be able to do is to mark down the location of this object. And we affectionately call this object Bob. So I'll just keep referring to it as Bob. So we're going to drop Bob. And as we drop Bob, we're going to fill in this table. And what this table is going to do is, what is the position of Bob at given moments in time. And so as I come over to here, the first thing I'm going to fill out are these two rows. These two rows, this row is the position of Bob. This is the time for Bob. And of course, I can't fill anything yet until we go over and actually do the experiment. But this is why I was saying this notation is probably a poor notation. It's an old notation. Maybe you've seen S for like the arc length in your math class and whatnot. So I'll just kind of put out here on the board distance. And so just keep in mind then, this S stands for the distance that Bob has fallen. And so what we're going to do then is fill in a table here and mark down where Bob is at different moments in time. And that's going to go right here on this table. Okay, and so we'll measure that. So with that in mind, I'll come back to the board in just a second, but let's actually run the experiment. Let's actually watch Bob fall, and let's go see the marks that we get. Watch, follow me to the back of the room here. And so I'll head around the lab room here, and I'll get over here to our equipment. And this is our equipment, and down here is Bob. And so I'll show you, here's Bob again. See, and so Bob's got this pointy little hat, but an important part is Bob's belt. Because what's going to happen here is I will put Bob up in the apparatus. This right here is a little electromagnet. And I can control it with the equipment here. I will first turn it on. And then when I turn the magnet off, Bob will begin to fall. And as you will soon see, there is some paper here. It's fancy paper. We call it spark tape paper. Because this little metal piece in front, which might be a little hard to see, both on video and even if you were in here face to face. It's hard to see till you get a chance to come over and look at it. But this metal wire will create a spark, and that spark will jump from the spark, and as Bob is falling, it'll go right to the nearest metal thing, which would be Bob's belt. And then the spark will go from Bob's belt through the paper into the next metal object, which is this metal rod behind it. And maybe I should just show you. All right, so here's the idea. And so the first button I'm going to push turns on the magnet. So I'll come over here. And as you can see, that holds Bob into place. Now, the experiment is really done with the next button. And so the next button, when I push it, first it'll turn off the magnet. And then second, this little machine will produce sparks. And here's where I want to make this clear. That our machine makes a spark every 60th of a second. But we are asked in the lab to mark Bob's spot every 30th of a second. And so the way we'll deal with that is we will just ignore every other spark. We'll just take the first and the third and the fifth and the seventh. Okay? And so that's why the procedures say mark Bob's position every 30th of a second, but our equipment is set up here for every 60th of a second. So that's kind of minor, but here we go. Let's watch the sparks and let's watch it fall. So here we go, push on the count of 3. 1, 2, 3. And I'll be curious to see the video and see how the sparks came out, if you could actually see them and hear them. But there are little marks on this tape. And from your distance, I'm sure you can't see them. Let me bring the tape a little bit closer. Because if this was a classroom setting, after you guys would come up here and drop it, you would then do what I just did. And then you would take this to your table and make your measurements. So I'll get a little closer here and see if the little dots will show up. Ah, here we go. So I'll just kind of scan across there, and so you can see the dots. Maybe I'll go to the beginning here. Whoops, wrong way. But the dots are really close together here at the beginning, and then they get further and further apart. And they're really tiny. So let me take this over to the desk. So again, you and I as partners, let's mark every other one. And so I'll circle around here to the front. And I'll just lay this out. And boy, some of them are really faint, but I think they're dark enough to actually see. And to keep me from knocking the paper around, the spark tape, I'm going to go ahead and tape both ends here. Get it straight. Okay, and I'll use the 2-meter stick here in a moment. But just so I can keep my focus here, I'm going to go ahead and make some circles here. And so maybe I'll go ahead, make a little judgment call on our first one here. Yeah, I'll go ahead and call that. So let's go first, the third, the fifth, the seventh, the 9. Ooh, we might have a little bit of an issue here. 1, 3, 5, 7, 9. Yeah, I think that's a false one, and that happens quite a bit. You'll see why this is a good thing about taking a lot of data. So I'm going to skip that one and go to here. And that will be one that I'm going to make a mental note as we start making our graphs. There might be something kind of weird right here. But skip one, go here. 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 Skip one, and whoops, went too far. All right. So let's then collect the data here together. And so we've actually done an experiment with a falling object, falling Bob. And so let's start measuring them. I'll start with the easier of the two, the time. Because the first dot is 0. The next dot, now I should say the next circled dot, okay, would be a 1/30th of a second. So I'm going to put a 1. Because if you look at your table, you will see that the author has put here, write down in units of a 1/30th of a second. So this is 1/30th, 2/30ths, 3/30ths, 4/30ths. And like I said, that's the easy one. We're not really even measuring anything. It's really the computer there that did it for us. So let me just count what I have here. I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of these. Okay, so I don't have enough room on the board here, but this goes down to 13. And so for you guys then, make sure you've put down wherever 13 goes, maybe right about there. So we're not filling in the whole page, just however much room we have, because our apparatus is only so tall. All right, so that's how much we have, and that's quite a bit. Okay, and so that's the time for a falling bob. Now, this column, the third column, as I said, is distance. And you'll notice that it says measure the distance in centimeters. All right, so following their lead, I'm going to grab this longer, and I think this is more than 1 meter, so that's why I grabbed the longer one. And of course, I need to find the centimeters here. Now, if you were in lab, I would ask you to look at this side, which is marked off in inches, and so I'd say ignore that. And then on this side, you will see it's marked in centimeters. It also has millimeters and meters on it, but we'll just get the centimeter part. And the centimeter part is actually the numbers themselves. So I'm going to lay this right here. And of course, in this fashion, you can't actually see the numbers, but I'll put them here on the board. Remember, you and I are working as a team here. And so I think that'll be some good readings. And so I'll just begin. So the first dot is the easiest one. I put it right at the edge, and it says 0. All right, so there's 0. The next one, it looks like I have about a 1.5 centimeter. So 1.5 centimeter. The next one looks like about a 3.8. So 3.8 centimeters. The next one after that is about a 7.2. So 7.2. The one after that looks like 11.7. 11 point, let me just check that one. Did I say 7? Yeah. The next one looks like about a 17.2. And as I mentioned, we need to go all the way down to 13, so that's number 5. And so let me just put here, maybe I'll come over here, number 6, go a little higher. Number 6, number 7, number 8, number 9, number 10, number 11, number 12, and then our last one, number 13. All right, so coming back over here, 17.2. Looks like this next one is a 23.1. So 23.1. No, my bad. It's 23.9. I want to mess you guys up. All right. So 23.9. Then it looks like 31.7. Double check, 31.7. And then it looks like 40.5. 40.5. The next one looks like 50.5. By the way, let me just pause right here, because if this was face-to-face, I would be walking around the classroom right about now and saying, okay, how's it going? Getting your data, good. And then one of the things I'd ask you is, are you seeing anything of interest so far? I mean, it's not that easy to see yet, but what you would hopefully notice is you're beginning to notice that the spacing between the dots is getting bigger and bigger, and that's kind of how I drew them there. And of course, what that would tell you then is they're going faster down here, which would tell you it's accelerating. And that is ultimately the goal here. As we talked about in the lecture, when you drop something with free fall, it does have a constant acceleration. But now in class, we said 9.8 meters per second squared. So in here, where we're doing things in centimeters, that would be 980 centimeters per second, each second. So hopefully that's what we're we're going to measure. That's this ultimate step, is to ask, hey, when you drop something, is it accelerating? And if so, then what is its rate? And so in class, the lecture that you just saw on chapter 2, I just told you that the acceleration was either 9.8 meters per second squared or 980 centimeters per second squared. And I just told it to you, knowing that we would come in here and measure it. So hopefully that's what you're beginning to see. You are beginning to see the dot's bigger space. That tells you it's going faster, so that does answer our question. It is accelerating. Now, until we study the numbers better, we won't get a number on what that acceleration is, but by the time you finish the lab, hopefully you'll be saying, yes, the acceleration that we measured in the lab is close to 980 centimeters per second. All right, well, back to our data. So this was number 9, and that 5 doesn't look very good. Let me do a little better. Okay, so 50.5, 61.4. 73.6. 86.7. And then finally, 6.7, we've got 101.0, I'll call it. So 101.0. Ta-da! Okay, so this is the raw data. This is just collecting the data that says what is the position and the time. Now, here's where you're going to start doing some work, okay? But let me help you along the way, okay? Is you're going to want to then follow the directions. And the first part of those directions say, get out your calculator and fill in the rest of this table. And so I have a calculator. I won't do the whole table, but I'll help you get started here. And I'll start with the easiest one first. And one that actually can be confusing just because of the way the table is laid out. This delta, as I mentioned earlier, delta stands for the time between each dot. So I think our table would look better if it had a box that kind of overlapped these two. It doesn't. So you guys can just move it up to here. But remember, what you're writing in this box, whether you move it up to here or move it down to here, doesn't really matter whether you move it up or down. What matters is what you're saying here is what's the time difference between these two dots. And that would just mean you take that number and subtract that number. So 1 minus 0 is 1. And that would be, and again, notice the units here, 1/30th of a second. But you'll see the same thing here. What's the time between these two dots? And of course, it's 2 minus 1. You won't need a calculator for that. That's just 1. And again, the same thing, 1. In fact, you could just go all the way down. And because the timing is done by a computer that makes the spark, it's always going to be 1/30th of a second. All right. Now, yours won't look like this, so let me clear mine off. Yours is going to look like this. You've got a 1 here, you got a 1 here, you got a 1 here, you got a 1 here. And that means down here at number 13, don't put anything, right? You can put an X or something. Saying, look, there is no time difference, okay? Because this is really between those two. So in other words, if we've got 0 to 13, that's 14 marks here, we would only have 13 here, okay? So we've got a time difference between them. See, and the same thing can be said here. This right here, this delta S, is, again, maybe you're getting the idea of the symbolism. The delta means the change. And so this would be how much distance did Bob travel between each of these dots? And again, the table would probably look better if it was positioned like this. So you could just say this minus this is the distance between those two dots. And then the same here, it would be between those two. And maybe I should get a calculator. Hopefully I won't make a mistake. 8 minus 5 is 3, and then 3 minus 1 is 2. Okay. Same thing here. If I subtract them, well, here I'll have to think a little bit harder. 12, I'll borrow from there. 12 minus 8 is a 4. And so 6 minus 3 is then a 6. Okay. Whoops. See, I knew I'd make a mistake. 6 minus 3 is a 3. I think I said, yeah, all right. Sorry. All right. But you want to continue on down, and that's what I'm going to let you do, and go all the way down. Now, again, for better or worse, your table doesn't look like this, so let me do this. Let me put the 1.5 here. Let me put the 2.3 here. Let me put the 3.4 here. Okay? But don't get yourself confused, because this has been a common source of confusion for students when I walk around the room, is trying to remember that this 1.5 is the difference between those two. It's just we wrote it up here. And so, of course, that means way down here on number 13, you can just put an X. But now, you can even see much better than before when it was over here. You will see that the distance between each of these dots is getting bigger and bigger and bigger. And it's during the same time frame, so that would tell me it must be going faster and faster and faster. And so already I'm seeing that this does have an acceleration. And so, as I said, this experiment is really one to help you kind of understand position and speed and acceleration. But it's also one to confirm what we keep saying in the lecture, that if you drop something, it has an acceleration, a constant acceleration, and its value is, and in class we keep saying 9.8 meters per second squared, but we're measuring in centimeters here, so it's 980 centimeters per second squared. And that's also what we're going to then measure before the day is over. All right, so again, I won't do all the math here, but let me also help you with this. This right here, again, this would probably be better if it was written as a kind of a box that is between these two. Because this little v means what's the velocity, and the little bar across it means what is the average velocity. And so we'll just take the distance and divide it by time. And that's why I wanted you to watch the lecture on this before you get started, because we know, and I'll just maybe put that right over here somewhere, but if we're looking at the average velocity, we just take the distance between those 2 points and divide it by the time between those 2 points. So what they want you to do in this column then is to take, well, how far did it travel between the 2 points? That's why we have this right here. That's the delta S. And how much time did it take? Well, that's why we did this column. That's the delta T. And so right here, they would want you to put, and here's where a calculator can come in real handy here. So I'll grab my calculator. But my distance would be 1.5 centimeters. And my time then would be 1/30th of a second. And so I will put 1/30th of a second. And let me give you another little caution. Because on my table, I've got the number 1. Okay, so here's the number 1. But remember, that means 1/30th of a second. So I don't want to put 1 for the time. I want to put 1/30. All right, so come back over here for this calculation. Here's what I would do. I would take my calculator, go 1.5 divided by, and I'll just do a parentheses, 1 over 30 close parentheses, and I come up with 45 centimeters per second. You could even simplify this before you even get out your calculator and flip and multiply. So this becomes 1.5 centimeters, and when you flip it, you get 30 over 1, like that. And so you just can multiply instead of divide if you wanted just to simplify your fraction before you jump into it. But either way, I don't care how you do it. You got your calculator in front of you. Go ahead then and get that number. So here's what this would say. I would put a 45 here. And of course, this would be centimeters per second. And again, I'll put it in this upper box, but please remember, I don't mean that the speed is 45 at this time. What I mean is between these two dots. So it started with no speed and went faster, faster, faster. And so the average over that little piece is 45. I'm not saying it's going 45 when the magnet was first turned off. I'm saying it averaged 45 during that length. That's why I think this table would look better with the little box down here. But that's not what we have to work with here. But it's easy to overlook that. Maybe I'll do the second one here just to make sure you get the idea. So the second calculation would look something like this. I'd get out my calculator and go, okay, the distance between these two dots, so between these two, is 2.3. So I'd go 2.3 centimeters. And then I'll divide it by a 30th of a second. Grab my calculator, 2.3 divided by a 30th of a second is 69 centimeters per second. So this is 69. Yeah, so it's going on average a little faster between the second and third dots than, or second